Okay, good afternoon, everyone. This is Allan Fulton, Farm Advisor up in Tehama County, Irrigation and Water Resources Farm Advisor and headquartered in Red Bluff. Welcome to the final webinar on putting weekly crop ET reports to work for you. Just real quick, little bit of caretaking here. This event is being recorded. Your mic is muted by default to prevent background noise, and we ask that you keep it that way. If you have questions, please type questions or discussion responses in the chat box. Catherine Jarvis-Sheen will be moderating the questions and passing them on to me. I'd like to say thanks to Clint Zhu and Rachel Palmer with the support unit from UCANR that is helping oversee this remote meeting and helping those of you that might need assistance with Zoom. Luke Milliron, Farm Advisor from Butte County, I think is out in the field working, but could be listening remotely by phone, so a shout out to Luke. So we'll go ahead and get started here. So as I said, this is the final webinar of a series of 5. This started almost back 2 months ago. April 3rd was the first tutorial, and the emphasis of that tutorial was to just navigate your way through these weekly ET tables that you receive from myself or from Catherine or other advisors, maybe in other parts of the valley, Central Valley. We talk a little bit about the basic ET concepts so that you have an idea where the numbers come from, the science behind it to support it. We speak to a little bit about how the tables let you consider how well your irrigation system is working and picking an irrigation efficiency factor to modify the weekly ET rate that we report in the table. And then we spent quite a bit of time at just how to do some calculations, using the numbers, converting them, and relating them to your irrigation system. We ultimately ended up on just the discussion of how to calculate a kind of upper limit on irrigation runtime for individual week to meet the crop water requirements. You can see the video link that's provided there and the PowerPoint that was used for that particular tutorial. The second tutorial, we revisited the crop ET reports, but from the soils perspective, and we spent time talking about how to assess the water holding capacity of your soils, of the deep-rooted crops like our orchard crops, and then how to relate how fast that that available water in the root zone is being used based upon the crop ET reports. We ultimately ended up kind of discussing, looking at some case studies of how we would maybe pair the ET reports and a water budget with actual soil moisture monitoring in the field to verify things. Kind of a two-prong approach. Again, the video links, PowerPoint are provided here. Tutorial number 3 happened May 1st, and the focus was on the tree, and we talked about why to consider the tree perspective, the connection between soil moisture depletion and the tree water or plant water status. And then we spent a fair amount of time using one of the primary techniques that we currently have, the pressure chamber and midday stem water potential, to actually assess tree water status directly. And then we looked at some case studies where we pair using the ET tables and a water budget along with the actual field monitoring of tree water status, and pairing them up to maybe have a little stronger approach at how we make our irrigation decisions. Just 2 weeks ago, we had a 4th tutorial. It focused on using these crop ET tables to help us manage young developing orchards. And the focus was on the first 4 years. The way we have designed these tables that we report to you, that we are pretty comfortable that those estimates that we provide in the tables are good for use on most orchard crops in their 5th year and older. We spend some time talking about why we're comfortable with that, and then some techniques on how to adjust these weekly ET estimates for smaller trees that you may have. And we spent quite a bit of time with doing examples and looking at it. So now we move into the final tutorial to wrap up of these crop ET reports. And I've titled it a Gateway to Advanced Farm Water Management. And hopefully by the time I'm done, you'll have a sense of why I titled this particular tutorial the way I have. So the topics I'd like to recover, or that I'd like to cover, are I'm going to spend a little time recapping the intent and content of these weekly crop ET reports. Part just to remind us what we may have forgotten, plus in case other new folks are joining us for the first time. I'm going to kind of take an approach how these weekly ET reports can be building blocks to working our way towards more advanced water management techniques. And then I'm going to spend about half the time discussing some new advances in irrigation scheduling tools. So to begin, for myself, I've been doing these ET reports for a lot of years, and I know Catherine's been doing them for 4 or 5 now, and there's kind of increasing interest in it. And I think what's driving it is we're trying to do this as a way to encourage routine thinking about irrigation management, provide some information on how the weather might be affecting the crop's water use and irrigation needs each week, just as a little nudge to just be thinking about it. Our goal is that in any production system, as hard as we try, we always have a weakest link. And our goal is to the best of our ability, make sure water management is not that weak link in your production system. And then, as I've already said, if you work with these reports and think about them often enough and maybe give them a try, there's a chance that they're going to kind of spur your own thoughts and thinking and open the gate to your interest in advanced water management. So kind of a recap about these weekly reports. We apply scientific ET concepts in a practical, informative manner for agricultural water managers of California. And we spent a lot of time in the first tutorial discussing these concepts. We work as a team, University of California Farm Advisors up and down the Central Valley of California, and scientists from the California Department of Water Resources to provide these weekly reports. The idea is for us to work with the science and do the necessary computations so that it's not a workload for you. We access real-time grass reference, that's abbreviated by ETO, data from several California Irrigation Management Information System weather stations, that's the acronym CIMIS. And we select the best available crops for crop coefficients, abbreviated as KC, to estimate ET for the major perennial crops grown in our region. Now, we don't report annual crops. It's just a tougher challenge to pin down the planting dates and different things that affect the length of growing season and things. And so it's more than we can do in a concise, simple table each week. The reports target specific agricultural regions. For instance, we report out of the northern Sacramento Valley from 4 different weather stations, and then we report from the southern Sacramento Valley from 4 other weather stations, and so on. We move down the northern San Joaquin Valley and further south. Each week, we provide an estimate of the crop water use for the past 7 days, a running total for the growing season, and an estimate for the next 7 days. Along with the ET estimates for the major crops growing in the Sacramento Valley, and we provide a weekly and cumulative accounting of the rainfall amounts so that they can be compared to the crop ET estimates. So just a few slides, a little reminder on what ET is. You can see this picture here. ET is something like on a day-to-day, we can't feel it, but we know by the mugginess of it that there's definitely moisture in the air and it's occurring. Essentially, it's evaporation of water off the soil surface of our irrigated lands, as well as transpiration from the water vapor leaving the canopies of our crops and driven by the hot sun that's beating down on it. So ET is water leaving the field instead of incoming, the opposite of rain, if you will. It's often unspoken, but its measurement area is on a per acre basis, or if you were in another part of the world on the metric system, it would be a per hectare system, or per hectare. So the reporting units are typically inches per acre, and again, it's typically just left as inches. Time steps can range from hourly, daily, weekly, monthly, or annually. For irrigation management, we report it weekly time steps. We'd like to do it more frequently, but it's just beyond our means. There are 150 of these CIMIS stations located statewide. They report hourly ET for irrigated short grass cover, like the one shown to the left in this picture. And there are 8 stations in the northern or in the Sacramento Valley area that we acquire our data from and report our tables to you each week. So what the grass reference ET does and does not tell us, it's a real-time measure of the crop water use for irrigated pasture. So if you're interested in trying to use ET measurements to help guide irrigation pasture, this is the simplest crop to use it for. It's a direct measurement. It's a standardized measure of evaporative demand for specific farming regions. I've already showed you the map of how the stations are approximately distributed evenly throughout the Sacramento Valley. It tells us about the seasonal changes in evaporative demand from spring, summer, fall. It alerts us to normal or unusual, how normal or unusual the recent weather has been and how it affects the evaporative demand. It does not give us a precise estimate of crop water use for all the other crops that we grow in our farming regions. And at times we can find unique microclimates that our weather station network doesn't represent well. In order to report ET estimates each week based on real-time regional weather for the major crops grown, we have to convert this grass reference ET to crop ET. And we do this by using research-based crop coefficients to estimate crop ET for each crop. And these coefficients are developed through various techniques and through a lot of research. And this is an example of almond. And you can see a weighing lysimeter that's in the ground here that is used to help actually measure the real-time crop evapotranspiration coming off these trees in this orchard. The crop coefficient is a ratio of the actual ET measured using these different techniques and against the grass reference, the short grass reference ET measured with the CIMIS weather stations. So now we'll walk through a little bit about just navigate our way through a report. This is last week's report for May 15th through May 21st, 2020. I chose it, thought it was a little more interesting to look at because it was a rainy week that week. So here's the date. We have 2 report formats, one that distribute by email, and then another that I will show you that's distributed or available online. So I'm going to use the almonds as an example. These dates that are in the parentheses are the dates that we observed as the bud break or the vegetative bud break or the beginning of canopy development for each crop. This is the date we begin measuring the ET and accumulating the records over the season. Down at the bottom of the table, we would have the past 7 days of precipitation reported, and then right below it, we would keep a running total, and that running total is from the earliest date that we start reporting, and it's usually based upon the almond leaf out date. You move across the table. In the case of for the northern Sacramento Valley, we're reporting these ET estimates from 4 different weather stations, one located in Tehama County, one located in Butte County, 2 actually, one near Biggs, the other near Durham, and then one in Colusa County. And just to kind of keep with the flow of things here, you can see the estimated ET for the past 7 days, 1¼ inches. You can see the cumulative from March 1st through May 21st as 9.2 inches, and then a normal year average for the next as an estimate of what could possibly be a forecast. And then here you can see, again, we're reporting the rain in Durham the week before last. It was a wet week, 1.69 inches. Typically, Durham is among the wetter stations that accumulates more rainfall during the springtime. And as you can see here, 4 inches. We continue and look and contrast this to the weather station in Colusa County near Williams. You can see that ET was higher, and since March 1st, the ET has been higher. The projection is higher, and you can see that the rainfall was very minimal. So during this wet week, it's quite possible have a person be using these reports, they might have been inclined to be doing some irrigation, or more likely than at the Durham station or the Butte area. This is how these tables are intended to help inform us and help us to think about what we're doing and why. The last thing we do, the bottom half of this table, we adjust for irrigation efficiency. And I'm going to just highlight the 90%. So what we're doing here is we're accounting for non-uniform application of water across the orchard, allowing 10% extra so that the areas we think get the least water get enough water. That increases the ET estimate from 1.55 to 1.7. Just as why did I choose the 90%? This is just a reference source by Daniele Zaccaria, showing that for surface drip, subsurface drip, and micro sprinkler, a 90% efficiency for newer and well-kept systems should be pretty reasonable. This is the online report format. You have 2 links for choice to look to the southern Sacramento Valley, northern Sacramento Valley. Here's just looking at the Colusa example. It's the same data, just a different layout. And in order to see other weather stations, you need to scroll up and down the web page to locate them. So you can receive your report and you've read it, and you have an estimate of the past 7 days of ET for your orchard. Now, what do you do with this information? Now, in some of the earlier tutorials, we worked through the arithmetic by hand. We had some examples for you to try your skills yourself. For today, I'm going to just use the calculators that we offer online to help and to show you, to demonstrate how we use the ET numbers selected from the table. I'm going to use the 1.7 number that we walked through and found at Colusa at the 90% efficiency. But in order to use the ET numbers and to arrive at an estimate of the upper limit of your irrigation time needed for it to match that ET, put it back, you have to know something about your irrigation system design. In this instance, it was a micro sprinkler system. Micro sprinklers put out 8.5 gallons per hour. There was 1 per tree, and there were 180 trees or 180 sprinklers per acre out there. You use this calculator or you do the math, and that works out that you need about 30 hours of irrigation with that system to put back that 1.7 inches of ET. And I managed to subtly click from one calculator to the other. There's the 0.056 or hourly water application based on the design. And then here's using the next calculator, putting in the designed application rate, the ET taken from the table, and seeing that this is suggesting an upper limit of 30 hours of irrigation for that week 2 weeks ago in Maxwell. All right, so I'd like to stop for a minute and give you a chance to think about this a little bit more and just raise the question, how can using these weekly crop ET reports help with your irrigation management? So, had consensus that using these reports can help us by providing a sense of how the real-time weather is affecting the water use by the crop. It can help us think about the irrigation efficiency, the water application rate, and relate that ET rate to the water application rate, and ultimately we can calculate a kind of an upper limit to help us guide what our thinking about how much water we might need for that week. So I wanted to touch on, that was the focus of our tutorial number 4, but it is possible, even though we report these ET numbers and emphasize that they are for mature trees of 5 years and older, it is possible to use these tables on younger trees. I wanted to pick up on a question that came up 2 weeks ago just for a minute. We can use these weekly ET reports on younger trees and make adjustments, but we need to be careful about it, especially in year 1, during the first month or 2 after the trees have been transplanted. There's a time in there after transplanting that these trees, whether it's a potted tree or bare-rooted tree, they tend to sit a little bit idle, and you don't see much in the way of new tree growth, new tip growth. And during this phase, and it can take some time, 4, 6, 8 weeks, kind of depends on the planting conditions and the weather. During this phase, in particular, it's much more important. The ET reports are pretty much of no use, okay? It's much more important to be out there in the field, digging in the transplanted area, in the soil, or even on the case of a potted tree, getting on the fringes of that potted soil and judging the moisture in there and looking for indications of new roots, much more important than using these ET reports. Once the trees are rooted and growing well, more like this, you can begin to start thinking about using these ET reports, more like the picture in the upper right-hand corner. But to do this, you're going to have to make adjustments for the change in canopy size. And the other little tricky part here is that as that first year you plant that tree, particularly in the higher rainfall areas, if you plant into a profile full of moisture, that root can grow out and explore that stored water. And as a result, once you get the tree going, the irrigation may not be as intensive because that tree can thrive pretty well on a lot of stored moisture. So just some suggestions on how to adjust these ET tables for younger orchards. This is an example of a third leaf prune orchard. We offer some just very general adjustment factors for tree age, based on tree age. And these are kind of the average percentage. So you would probably want to realize that's the average, and when the tree is coming out of dormancy that year or smaller, and that it's going to maybe be 10, 15% lower at the start of the season, and then as the tree grows and reaches the end of the season, that number might be 10, 15% higher than the average. So you need to kind of recognize that's built into these general adjustment factors by age. Now, I'm only showing for Prune here. In the tutorial number 4, I provided other similar tables for almond and walnut. The other alternative is that you actually assess the canopy, how big the canopy is. This can be done at noontime by assessing the amount of shaded area on the ground. This can be done by either on-the-ground techniques or even using aerial techniques. In this case, when we gridded this out, this was about 41% canopy shading is what this represented, which matched up very closely, 67% adjustment factor, matched up very closely with the age-based. So to use this adjustment and to use our tables, you would go to, I come over here to Prune in this instance, Colusa County 1.7 inches for 5-year-old tree or older, or a full-bearing tree. Adjust 1.7 by 6.67, being that 67% right here. So I reduce this to 1.1 inches. I adjust the 1.1 for a 90%. Well, I take the 1.9 down here that's adjusted for the 90% efficiency. I multiply it by 0.67 and I come up for 1.3 inches of ET to build in a factor for the irrigation efficiency. So, and then I go back to my calculator, weekly crop ET. This was single line drip, so the water application was lower, 0.03 inches, comes down back to 43 hours, maximum or upper limit of irrigation needed. So I wanted to take a minute in case you're thinking about what do we mean by maximum irrigation runtime? What does this mean? Why is it quantified like that? I want to take a second and kind of answer the question and also begin to make a transition to how these weekly ET reports can kind of be a building block that can lead us to kind of deeper thinking about our water management and maybe even questioning or wanting better information and tools. So what's going on? If we just irrigate according to the ET losses and the applied water, and you take that wholeheartedly, that this 43 hours, and we don't consider in-season rain that can fall during that week of ET, stored water that's available to the tree, it's quite possible, even after adjusting for irrigation system efficiency, that 40 hours of runtime is too much. As we think through this and as we try to use these ET tables, we start to think more and learn more about things like the tree physiology, questioning what is really the effective root zone of the tree, what's the water holding capacity of soil, and more. And so the reason that I kind of quantify maximum hours, that maximum hours is based on the simplest of approaches, taking the ET loss, counting the irrigation system performance, and assuming you have to put all that water back on through the irrigation system, which might not be a good assumption, especially if you're having issues with trees that are showing signs of root diseases and decline from possibly too much irrigation. In most field situations, applying these weekly reports of ETC with your knowledge of your irrigation system will help assess the upper limit of irrigation and the amount of irrigation run time needed each week. As you learn, though, as I've already discussed, you may want more precise information and start down the path of advanced water management. So let's take a second and kind of think about this a little bit more. How can receiving and thinking about these weekly crop ET reports help me build my irrigation management skills? Okay, so I'm glad that in writing these questions, it's sometimes hard to be creative and think about coming up with questions, but I'm glad that we have some consensus here that these ET reports can cause us to think a little more deeply and maybe challenge us to keep developing our skills in irrigation management, maybe enjoy some of the fascination that comes with it as well. So now we're going to spend the rest of the time just talking about what are some of the advanced irrigation scheduling tools that are out there. I've divided them up into 3 categories. One described as soil water balance modeling. The major contributing scientific disciplines are biometeorology, engineering, and sometimes plant physiology. And if I'm forgetting others, I apologize. Second category is soil water status monitoring, which is soil moisture monitoring largely birthed out of the soil sciences and agronomy. And then there's the plant water status monitoring, heavily encouraged by the horticultural sciences, the plant physiologists, and gaining some interest among the engineering realm. It's becoming more common to integrate these different approaches, seeing them each for their strengths and limitations, and trying to capitalize on their strengths and minimize their limits. Some possible features of a soil water balance model is that one is probably going to be definitely computer driven. Well, actually, we'll talk in a minute that maybe there's an exception to that. The most robust will have a GIS interface. Oftentimes, they'll have the ability to bring in soils maps. They'll almost always be able to draw your field boundaries. May be able to even mark different critical infrastructure. They'll tend to lean towards using aerial remote sensing type, such as canopy temperature, either ground or aerial methods of measuring canopy fraction. There could be some crop phenology built into it. I'll give you an example that's definitely building in nutrient management elements. And then you'll see some familiar things that we've talked quite a bit about. They'll include applied water, rainfall, and ET, crop ET. Tend to maybe starting to build in more on the way of fertilizer applications, and some of the more robust are focusing on providing record keeping and reporting capabilities. These are a couple examples. There are numerous ones out there. One of them that I've highlighted here is called CropManage. Actually developed by one of our farm advisors within the University of California, A&R, Michael Kahn. And this is a irrigation scheduling and nitrogen management model and tool. And this other one, IrriWatch, is one that originated in the Netherlands, and I am aware that it may be finding its way into California and the other areas of the United States. Okay, so let's take a second here and do another knowledge checkpoint. And I just want to pose the question, by using the weekly crop ET reports and comparing weekly and cumulative ETC rates to applied water, rainfall, and stored soil moisture, do you think you are applying a very simple form of a soil water balance model? So this question generated a little more thought and a little more curious responses and interesting responses. And yeah, I don't know that there's a right answer here. I know in myself, I posed the question, I probably do think about it a little bit as a very simple model in the sense that really everything we have that we're working with, other than the weather stations, the ET-based weather stations, they're all kind of estimates and our best estimates that we can make, and we're trying to pull different pieces of the irrigation system together to arrive at a decision. And so from that standpoint, I kind of think of it as a very simple model. But anyway, definitely, if you get the reports and think about your irrigation system, it will definitely cause you to think more deeply about what's going on out there. Okay, moving on from the modeling, go to the next kind of category, and that is monitoring soil water status. These are familiar sensors. On the left, watermarks. On the right, capacitance probes that are commonly found on farms in California, as well throughout the United States. Soil moisture monitoring is, at the moment, the most widely adopted irrigation management tool across the United States. Roughly between 20 and 30% of farmers in the leading irrigated states report using some form of soil moisture monitoring. The advances in soil water status are focusing on the capability to monitor larger volumes of soil and cope better with soil variability and uncertainties about effective root zone. They're still striving to improve the accuracy in measuring the volumetric water content in particularly heavy soils. Some of our techniques tend to overestimate the water content in the soil. And so to use them, we really kind of have to use them in a relative sense opposed to an absolute sense. There's a definite interest to bring you soil moisture monitoring capabilities at a lower cost. And there's an interest in integrating the soil moisture monitoring capabilities with the soil water balance models to correct and affirm, field validate things. This is just an example of one research effort that I was able to observe that took place in Oregon State University, where they were looking at using fiber optics and heat pulses to get three-dimensional and larger areas of soil moisture measurement, as shown on the graphic on the right. I'm not going to attempt to try to explain how it works. To my knowledge, I don't know that it ever came to fruition. It's just an example of people trying to get creative and come up with improved devices. This is also an example that we're working with a little bit in Tehama County this year. Professor Isaiah Kaseka and his students in the lab are working on some farms in Tehama County. This is a resistivity sensor. I had a chance to see it in operation a little bit in the winter. You can see the orange cable going across the couple rows of trees there. They are wired to steel rods that go down into the ground, and then they send an electrical current through this cord down the rods, and they're measuring the resistivity over a very large cross-section of soil, as showing on the right-hand side of the picture, approximately almost 7 to 8 feet deep, and again, across 2 tree rows, which was in this case about 60 feet. And so it's an example of trying to pursue better soil moisture monitoring techniques. Moving on, we'll spend the rest of the time talking about advances in tree or plant water status monitoring. Basically, we can look to ground measurements, or we can look to aerial remote sensing measurements. So, as most of us know, our conventional measurement of plant water status at the moment is pressure chamber and midday stem water potential, shown on the left. This is considered a direct measurement of plant water status because what we're measuring is the tension inside that tree. Our technique is such that we're measuring the water tension of the scaffold xylem, denoted there by the red font. But so we're essentially trying to, again, measure the energy the tree is exerting to get its water as a method of quantifying crop stress. So if you have any experience with it, you know it can be a bit labor intensive. We're interested in automated techniques that, one, help us minimize the manual labor nature of it, but more importantly, give us a more complete picture of what's going on. High frequency, almost continuous measurements that we can get a very full picture of the stress levels, the ups and downs that our trees and vines go through. There are currently 2 sensors that I'm aware of that measure directly the equivalent of stem water potential of the pressure chamber, an Israeli company called Saturas, and a company and a technique that was birthed out of Cornell University called FloraPulse. They're both active in California. Ken Shackle, professor at UC Davis, has given me a chance to work with them and has been a lead scientist in this technique within the university. And I just refer you to a trade article where he talks about this, his experiences in wine grape. I've also borrowed a couple little technical examples from Ken, a paper he wrote. It's cited down here. It's a annual report to a funding agency, a funding group. And what we're seeing here is the stem water potential measured with the pressure chamber on the horizontal axis. And we're seeing the stem water potential measured with the continuous sensor. I believe this was the FloraPulse sensor in this case. The numbers next to the dots are the number of weeks each sensor was in operation. And then these are just point-in-time comparisons. And you can see a definite, nice correlation between the 2 techniques. This is an example of data used, taken again, I believe it was with the FloraPulse sensor. It was done in French Prune in another area of the world. And so you can see the dates are not what we're accustomed to. In this case, the grower took pressure chamber measurements daily on the same trees that the sensor was placed in. And the orange dots are the manual measurements. The black line and the points are the sensor measurement, and the points correspond with each other. And you can see pretty good mirroring of each. And then in this particular area, they were going through drought, severe drought this year, and they started just didn't have the water to respond to what the sensors were indicating. And the thing we started noticing was that once we started getting pretty high stress levels, we didn't see quite as tight of a relationship between that measured with the pressure chamber and that measured with the sensor. And that's still being evaluated as to why. The good news is that the sensors seem to work quite operable within the management ranges that we would think would be ideal for crop performance. So kind of changing up and moving away, you'll hear some, well, I've already listed that there are sensors out there that don't measure stem water potential or the plant water tension directly, but measure something that responds to it. And this is a dendrometer. There is at least one company out there that's actively marketing a dendrometer and helping growers to the extent they can. And just give you a little feel of what this is about. It kind of takes us back to when we learned about the tree age rings. Okay, the dendrometer is measuring the growth of that tree ring each year. From spring to fall, we measure about 6,000 to 8,000 microns, which is somewhere on the order of 1/4 to 1/3 of an inch of growth, trunk growth over the season. And you see all these little zigzags in the curve. Those actually turn out to be very important. If we zoom in at a higher resolution, the data looks like this. you see ups and downs. They are diurnal ups and downs. And you also see the slope of the lines. The general slope indicates that the trunk growth rate in general is good and not under stress in this instance. As it flattens out, it's an indication of more stress. More importantly, what we're interested in is the day-night shrinkage, trunk shrinkage. And this has to do with the tension of the water, the vacuum suction. And the more tension, the higher the pressure chamber measurement, the more suction, the greater the shrinkage of the trunk. It's that amount of shrinkage that correlates most closely with stem water potential. And then I've already touched on this, but downward trends of growth would suggest, would be interpreted as a period of stress. Now, the areas with the least trunk shrinkage probably correspond with the highest rates of ET and the lowest levels of crop stress. In our work in walnut, you can see when we looked at calibrated dendrometers that were calibrated to stem water potential, we saw pretty decent correlation. Here you see the stem water potential of two different dendrometers, and you see a pretty decent correlation. They do have different slopes and for each sensor in each location, but in general, pretty similar and usable. When we used the dendrometer to see if it could detect, would trend in the same ways as our pressure chamber measurements and would respond after irrigation, it tended to pass the test pretty well. Here, the blue line represents one irrigation regime where we started irrigating earlier in the spring versus one that we delayed. The sensor was effective at picking up on the differences in the two regimes. And again, the sensor was good at detecting the lowest stress points and detecting the recovery stress points. And here you can see the value of the sensor, if we can get it, getting these continuous trend patterns, insights into the stresses the tree's experiencing. Okay, we're nearing the end of our hour, and so I'm getting close to the end. The last piece that I want to talk about are aerial methods of evaluating tree water status. That would involve using either drones, sensors on the bottom of fixed wing planes, or possibly looking at satellites. At the moment, there are not very many satellites that offer thermal measurements, and there are some issues on filtering the thermal images for cloudiness and things like fire and smoke, and so something to be considered. Here, just share with you a little experience with, that we've had trying to learn about this using infrared sensors on the bottom of fixed wing. This was working in cooperation with Series Imaging. They were very gracious and supported us with this to the best of their ability. We had an experiment in nonpareil almond where we had variable rates of ET. We carried out this experiment for 6 years. And so we had, these are roughly half-acre plots that were irrigated according to these ET rates. And we could use this experiment to fly over, and sure enough, this is an example from July of 2015, the thermal imaging could pick up very well. Here you can see the yellow and reds indicating higher canopy temperature, corresponding with our lower ET. You can see the blue corresponding with our higher ET. And then you can kind of see the mid-ranges. Not much blue, not much yellow, more green. Same thing if you come over and study the patterns on the other side. So there's definitely an ability there to detect some things with the aerial infrared imagery that relates to stem water potential. However, when we tried to say, can we predict stem water potential measurements from the aerial imagery, you'll see that while there's a decent correlation, I didn't give it the correlation coefficient or the statistics behind it, but typically on the order of around 60%, 70% would be high. You can see even with that kind of scatter and fit, our ability to predict stem water potential, it's a stretch, because for any point on the line, we can be 2 or 3 bars, even 4 or 5 bars off sometimes. The other thing that we kind of notice is that here you have the black dots represent a flyover in April of 2015, July 2015 are red, and the blue August of 2015. You can see that that there is a shifting relationship to stem water potential over the season. That it's kind of hard to apply the same relationship. The other thing I wanted to point out, I have a now retired colleague, Blake Sanding in Kern County, has worked with this, has had a very good experience with this. What we did learn from this, that our general response lines are pretty similar, whether it's in Kern County or Tehama County on the opposite ends of the Sacramento Valley, the relationships and responses are pretty similar. This dotted line right here is from Blake's data, which is not shown here, and this dashed line is best fit line based on the Tehama County data, which is all of these points on the graphic. So I failed to kind of discuss the theory behind this a little bit, but the idea is that water stress causes tomato closure, and this reduces transpiration and cooling of the leaves. This also reduces the carbon dioxide in the tree and going into the tree. And so with the aerial imagery, they're measuring the thermal temperature, normalizing it for the ambient air temperature around it, and then they have a algorithm that converts it to CO2 conductance. So we're going to wrap up here, last knowledge checkpoint, and 1 or 2 more slides. So we have pretty good consensus that we probably would like some field verification in one form or another to back up our ET-based irrigation scheduling using our weekly ET reports. And a little more interesting response as to what might we be interested in using to back up our ET-based scheduling. And one person interested in the more sophisticated soil water balance models, 3 in improved soil moisture monitoring devices, 2 in the ground-based sensors of tree water status, and 1 in the aerial, and then the largest group showing an interest in more than one of these approaches. So thank you for taking the time to do that, and appreciate the feedback. So I think this is my second to last slide. And so when we start talking about technology, we know it's hard to keep up with it. It's hard to know what's the right thing to do and know if it pays back. And so just some suggestions. See irrigation technology as a continuum, something that constantly and gradually changes. It doesn't have clear dividing points. And we're going to kind of have to live with that there's always going to be a level of uncertainty. Begin with the simpler concepts and technologies, and essentially that's what you're doing by subscribing to these ET reports and giving them some thought each week. Take time to establish proof and concept, return on your investment, and to assess the robustness of the approach. And then try technology slowly and on a partial scale. And oftentimes some of these things you can start on a manual approach, say, for instance, the pressure chamber, if you like what you learned from the stem water potential, then maybe your interest in the automation will come after that. So I'll end with thank you for those that joined us today, and have a good weekend. If there are any questions, I'm happy to stay on the line. If there are no questions, have a good weekend.